All right, so we're continuing on with our discussion of limits, and this next example is going to be another case where a limit fails to exist. We talked about the Heaviside function in the last section, and in that example we showed that the limit failed to exist. Let me see if I can find that page again. The reason it failed to exist is because we were specifically looking at the limit as t approached 0, and we had a break in that function. We had a left-hand limit that went to one place, a right-hand limit that went to a different place, and so the two-sided limit did not exist because these two one-sided limits or one-handed limits did not agree with each other. But there's other ways that limits can fail to exist. And it occurs a little less often, but this one happens as well. We're going to call this an oscillating discontinuity. You actually don't need to know that term quite yet, but the function that we're looking at is this one, sine of pi over x. And this is what the graph of that function looks like, but let's ignore that for a second. I want to just investigate this. Let's suppose we wanted to take a numerical approach to solving this limit. Remember what that would mean. That would mean that I'm looking for values of x that are close to 0 on either side of 0, and I want to plug them directly in for x, and then do that a bunch of times, create sort of a table of data, and then use that as a way of kind of guessing what this limit would be. So let's plug in some values, and rather than plug in decimal values, I'm going to plug in fractions. So let's see. Let's try plugging in. Well, let's call this function f of x first of all. Let's say f of x is equal to sine of pi over x. What if I were to plug in, let's just say 1. What is f of 1? Okay, well, f of 1 would be equal to sine of pi. That's pi over 1, right? That's where the 1 goes. What is sine of pi? Well, we know that's equal to 0. Okay, you need to know your unit circle, obviously. Let's use a value of x that's closer to 0 now. Let's use, instead of 1, let's use 1/2. Okay, that's equal to sine of pi over 1/2, but that's the same thing as multiplying by the reciprocal of 1/2, which is 2, sine of 2 pi. We know what that's equal to as well. That's equal to 0, right? What if I do 1/3? F of 1/3, that's equal to sine of, well, I could do something similar here. Pi over 1/3 is the same thing as 3 pi. That's also equal to 0. It kind of looks like this limit is going to be 0 because every time I plug in a number that's closer to 0 from the positive side, I keep getting the same thing. I keep getting a 0. So does that mean that this limit is equal to 0? Not necessarily. Let's try something else. Let's try plugging in a different number. Okay, so this could continue. I could keep doing this. Let's try something else. Let's try plugging in, let's say, which one did I want to do here? 2. Okay, f of 2 is equal to sine of pi over 2. Well, that we know is equal to 1. Right? What if I plug in, it's going to seem like I'm coming up with these fractions from sort of arbitrary places, but what if I plug in 2/5? Okay, that's closer to 0 than 2, for sure. So our inputs are approaching 0, which is what we're trying to do. This is equal to sine of pi over 2/5, or this is the same thing as sine of 5 pi over 2 when I simplify that input. But what is the sine of 5 pi over 2? Well, if you remember your unit circle from trigonometry, 5 pi over 2 is coterminal to pi over 2, which means even though they're different numbers, and technically, you can think of them as different angles, if you were to look at those two angles within the unit circle, they would appear to be the same. So the sine of 5 pi over 2 is still equal to 1. Okay, so what if I plugged in, say, 2/9? That's definitely closer to 0, right? That would be equal to sine of, again, I could do the same thing. It ends up being 9 pi over 2 here. What's that equal to? Well, again, this is coterminal to that angle. It's still going to equal 1. And if you notice, I could create a pattern here. You could probably figure out, how to find the next few numbers in this pattern, but I could continue approaching 0 using different choices of my input and get a 1 every single time. So these don't appear to be agreeing, and you'll notice I only used positive values. I didn't approach from the negative side, but I could use the symmetry. Sine has odd symmetry to kind of arrive at similar results. Remember, f of -1. If you're thinking of the sine function, which has odd symmetry, this is the same thing as negative f of 1, which would be equal to 0 still in this case. And I could do something similar for all of these. So I could use my positive inputs to determine what happens with my negative inputs. But that's actually not even really necessary. My numerical evidence appears to be pointing me in two different directions. As I approach 0 using one specific selection of inputs, my limit appears to be going to 0. If I use a different selection of inputs, my limit appears to be going to 1. And it turns out that if I'm careful about how I choose these numbers, I can actually do the same thing and find different values aside from 0 and 1 that this keeps happening with. And if you think about what's really happening here, looking at this graph, this function is oscillating faster and faster and faster as x approaches 0. Now, the function is not defined at 0, because if you look, pi divided by 0 is not defined. You're dividing by 0 there. But we can approach 0 as closely as we want to, and the graph is showing that the function just keeps bouncing back and forth between -1 and 1 at an increasing rate as we get closer and closer to 0. It's not squeezing down to any specific number between -1 and 1. It's just oscillating infinitely between the two of them. So this is, like I said before, a less common kind of example where a limit fails to exist, but it can happen in this way as well. Okay, let's do another one. This time I want to use a table to determine this limit here. So this is another numerical example. You'll notice a lot of the examples I've been doing, x has been approaching 0. That's not necessarily going to be the case all the time. Up here in our graphical example, we approached things other than 0 as well. It just kind of so happens that this example has x approaching 0, like some of the previous ones. But I would want to create a table here. And I'll use this example to kind of show you the need to be careful with limits. So let's do x, and our function is cosine of x over 25,000. Okay. I'm going to plug in 1, 0.1, 0.01, 0.001, 0.0001. I'll just stop there. So here we're approaching 0 from the positive side. I could also do negative 0.0001 and basically the negatives of all of these like we did in our last numerical example. But I'm not going to need to do that. The reason why is because this is an even function, which means that cosine is an even function. If I were to plug 1 into this function, I would get the exact same output as if I plugged -1 into that function. And the same would be true for any other thing I plugged in for x. If I plug in 0.001 into this function and get an output, I would get the exact same thing if I plugged -0.001. That's what it means for that function to be even. So if I put in all the negatives here, I'm just going to get repeats of all of these numbers. I don't gain any new information that way. So again, this would go into a calculator. So I'm not going to do this by hand. I'm just going to give you my calculator output. 0.00002161. Okay? Looking at what we're getting here, we're already getting a number that's very, very close to 0. It's tempting to look at this and think, shoot, I'm probably going to have a limit of 0. Let's get some more information or some more data down here. The next value I get is 0.0000398, and again, these are all rounded values because otherwise they go on infinitely. This is my next value, 39998, 0.0003, 1, 2, 3, 4, 5 of those 9s there, 8, 0.00003, and then how many did I get in this one? 7. 1, 2, 3, 4, 5, 6, 7. So these are the outputs that I was getting from my calculator when I was doing this numerical approach to this limit. And at first glance, you might look at this and think these are all really, really small numbers. You know, they all have 4 zeros before we get a non-zero digit after that decimal point. When you see really small numbers like this, it's sometimes tempting to say, I think that limit is 0. It appears to be approaching 0. But if you look more closely, that's not really what appears to be happening. Ignore the 4 zeros in front of all the non-zero digits for a second. I have 2161, 398, 39998, 3999998, 399999998. There appears to be some kind of pattern here. We appear to be stuck at 3 in our 10,000ths place, and then we keep getting this long string of 9s here. If we expect this pattern to continue, I'm expecting 3.99999, a whole bunch of 9s to appear in my next output. So what does that actually appear to be approaching? Well, these 9s are essentially going to kind of round things up a bit, and I think that 3 is going to end up becoming a 4. So this appears to be giving me a limit of 0.00004. Okay? Now it turns out that is the exact limit in this case. And even though my numerical approach doesn't guarantee that I got that right, there is something interesting that happens here. In the other cases where we did kind of the graphical and numerical approach with a function that was defined similar to this one, so kind of like a rational function of sorts where we're dividing by something, we looked at that and we said, what would happen if you actually plugged that 0 or whatever that number is directly into that function? And in those previous examples, we ended up with a divide by 0 error where we're getting 0 divided by 0. So plugging that number directly into the function did not work. We had to do either the graphical or the numerical approach. Here, though, what happens if I plug a 0 in? Well, cosine of 0 is equal to 1. And plugging that number directly into this will give me 1 over 25,000, which is exactly equal to this decimal right here. This is an example where we're taking a limit of a function as x approaches a number for which that function is continuous. And again, I mentioned the word continuous, but we haven't really defined it yet. And I don't want to give a definition of it yet because we're not at that section in the book. So that's more of a preview than anything. Okay, let's keep going. Another way that a function can fail to exist is it can do what we call approaching infinity or negative infinity. I really want to be careful here because we're going to be using this symbol infinity here, and it's showing up as if it were the answer to a limit problem. And it can be very easy when you're first learning calculus and start using the symbol for infinity to start thinking of infinity as a number. I want to say with no uncertainty here, infinity is not a number. We're not quantifying it here. This is just describing the behavior of a function, and that behavior is something that we're going to see in some examples. So let's just get to the definitions here. Let's just say that f is a function that's defined on both sides of a, but maybe not at a itself. We say that the limit as x approaches a of that function f of x is equal to infinity if the values of that function f of x can be made arbitrarily large, meaning as large in the positive direction as we want to make it, as long as we get x to be sufficiently close to a, but not necessarily equal to a. There's some similarities and some differences that you might notice between this definition and the first definition that we gave for just a regular limit. So I'll let you compare and contrast those. We have a similar definition for an infinite limit that approaches negative infinity. In this case, the function f of x will be made as small as we wish to make it as x approaches a. And in this case, by small, we don't mean close to 0, we mean very, very far in the negative direction. So to make this a little bit more concrete, let's look at an example. Here's a function that we're going to be looking at the graph of. F of x equals 2 over x minus 1 squared minus 1 over x minus 3 to the 4th power. And I just graphed this in Desmos. You can graph it in a graphing calculator if you want. What we're doing here is we're being asked to evaluate a couple of limits. First of all, the limit of f of x as x approaches 1. Now here's 1 right here. And you should know by now what this blue dashed line means. This means that we're looking at an asymptote. So really that's what these infinite limits are doing. They're describing vertical asymptotes. Look at what's happening on the left side of, or on either side, I guess, of 1. On the left side, our curve seems to be skyrocketing upwards. So the values that we're getting for the points on this curve, the y coordinates in particular, are getting larger and larger and larger, and they don't appear to be slowing down. They don't appear to be leveling out at any point. They're just increasing infinitely upwards. Same thing's happening on the curve to the right of our asymptote here. We're approaching infinity. This curve, as our x values get close to 1, the y values are just skyrocketing in the positive direction. This is what this first type of limit is describing graphically. As x approaches 1 in our case, the function is approaching infinity, which means it's getting ever larger in the positive direction and never slowing down. If I look at the limit as x approaches 3 instead of x approaching 1, I can see that my curve, here's 3 right here, my curve on either side is also approaching an asymptote, but this time moving down towards that asymptote instead of up towards that asymptote. We would say that this curve is going towards negative infinity, which again, there is no such number as negative infinity. So it's really just a useful label that we can put on things that do this, okay? We have similar definitions for left and right hand limits as well. So for example, the limit as x approaches a from the left is equal to infinity is describing what this function is doing only to the left of one of those asymptotes. So you know, sometimes you get a case of a function, let's say something like this, where maybe a hyperbola, you know, maybe the function looks like that. If that's a right there, then the limit of f of x, our function f of x, as we approach a from the left would be infinity, but as we approach from the right would be negative. I just realized that's off screen. As we approach from the left, we're going towards infinity. As we approach from the right, we're going towards negative infinity. So sometimes we need to have those one-sided limits if our asymptote is doing something different depending on the direction that we're approaching it. Okay? All right. This is the last part of this lecture here, and this is basically summarizing exactly what we just talked about, but with some images to look at. So again, the key thing when we're talking about these infinite limits, if at any time, whether it's a two-sided limit or a one-sided limit, left-hand or right-hand limit, if the limit is approaching infinity, then graphically that corresponds to a vertical asymptote. And here are a few cases that are broken down. I already kind of described that a little bit on the previous page, but that's what we're looking at with these infinite limits. Okay, so that's going to wrap up section 2.2. In section 2.3, we're going to be looking at much more efficient ways of evaluating limits with functions that are given in an algebraic representation. So we'll talk more about that in the next section.